We'll now look at the relaxation method for solving eigenvalue problems. Again, the concept that we'll cover here is a lot similar to what we have covered from the boundary value problems. So before you do a relaxation method, what you need to do is you need to discretize your domain. Okay, so right now you have your domain of x, which is from 0 to 1. So you need to discretize your x domain. So if this is your x direction here, what you do is you just discretize them into a few number of segments or intervals. So in this case, let's say I'm just taking 4 intervals. Okay, so I call the first point x0, second one x1, x2, x3, and let me just extend it further. What you what you get here will be x4. Okay, so the width of each interval is the same, which is h. You can also use non-uniform segment widths, but then that would not be efficient anymore. So what you need to do with the relaxation method is you need to approximate the second order derivative which appears in this equation using the Taylor series approximation. So I will refer you to the lecture notes in lecture 15 to find out how you do it, but I can basically write them here as y double prime I is basically given by yi minus 1 minus 2 minus 2yi plus yi plus 1, and that would be divided by h squared. Okay, so this is the second order derivative finite difference approximation obtained using the Taylor series. So what we need to do is we need to apply this approximation to each interval that we have. If you look at this term here, each approximation of your y double prime requires 3 points: your I minus 1, I, and I plus 1, which means for every interval you need to account for 3 points here. So our first interval, which is given by red here, I can write my y double prime here as y0 minus 2y1 plus y2 divided by h squared plus lambda square. Y would be y1, and this would be equals to 0. Okay, so this is from my application of this approximation into my governing equation here, so that d square y dx square is just written by this expression here, and lambda square y1 is just the value of this lambda square y. Okay, so this is for my first interval. For my second interval, I'll need these 3 points here, okay, which is x1, x2, and x3. So if I write that out, what I'll get is I'll get y1 minus 2y2 plus y3 divided by h squared, and you'll have lambda y2 square is equals to 0. So this is for your second interval. For your third interval now, you need the last 3 points. Okay, so what you get is you get y2 minus 2y3 plus y4 over h squared plus lambda y3 squared, and this would be equals to 0. So in the boundary value problems, what we do is any known values that we have, we bring to the right hand side of the equation, and any unknown values we bring to the left hand side. In your eigenvalue problems, you don't do that. What you do instead is you move your lambda square y term to the right hand side. Okay, and any known values you just replace them into the 3 equations that you have appropriately. So if you look at our problem, we know that y0 is equals to y1 is equals to 0. Okay, and we have discretized our domain into 4 segments. Sorry. So that means you have x0, x1, x2, x3, and x4. So x0 at x0 your y0 would be 0. Okay, and at x4 your y at x4 would also be 0. So if you look at your first equation here, y0 is basically 0. So you can rearrange this to give you 2y1 minus y2 over h square is equals to lambda square y1. Okay, so this is the first equation. If you look at the second equation, everything here is unknown because 1, 2 and 3 here are unknown values because they are your interior values. So you retain them as before, and what you get after you rearrange it, you get minus y1 plus 2y2 minus y3 is equals to h squared. Okay, and for the third one, y4 is known because the value of y here is equals to 0. So putting that into the equation and rearrange, what you get in the end is minus y2 2y3 over h squared plus is equals to lambda square y3. Now you note in the beginning of this recorded lecture, I've mentioned that eigenvalue problems are basically written as such. Okay, so what we have done here is basically to write our equations in this form here. So you can see that on this right hand side we have our lambda square y, which is given by this lambda square y terms here. So these three equations can be written as a system matrix form, which is tridiagonal in nature. So what you get is you get this system here. Okay, so you have your 2 over h squared minus 1 over h squared 0, and then for the second one you have minus 1 over h squared, 2 over h squared minus 1 over h squared, and likewise you have 0 and 2 over h squared. So this is your matrix A, and you have a vector of unknown values, and that would be given by your lambda square y1 y2 and y3. Now I know this is similar to this. Okay, and you can also rewrite this as a minus I lambda square y is equals to 0. So you may be tempted to just inverse this matrix to find out what is y, but that is not possible because for one you don't know what is your lambda here. And for the second one, if you inverse it and you bring it over here, this is a vector of 0 values. So anything that you multiply by 0, you get 0, and what you get is your your trivial solution. Okay, so you don't look at this way of solving it. Instead, you make use of the built-in functions of MATLAB. So what you have is you're using this command here to solve your eigenvalue problems. Okay, so this is a statement that you use in MATLAB. V will refer to your eigenvectors, while E will refer to your eigenvalues. So when you call EIG and A is your this system matrix here. So if you call EIG A, the output of your MATLAB statement would be the eigenvectors and their corresponding eigenvalues. Okay, so I won't go into the details of the MATLAB implementation. You can read through the lecture notes yourself. The thing that I want to point out is when you're using the relaxation method, the number of intervals that you have define your accuracy. In general, the more intervals that you have, the higher your accuracy. Of course, there is always a limit that on the number of intervals that you can use before your numerical scheme breaks down. Okay, so from the lecture notes you can see that with only 4 intervals here, the results is very poor when you compare it to the shooting method. But when we keep increasing the number of intervals or internal points, the percentage error reduces and it agrees more to the shooting method. Okay, so just go through the lecture notes for the examples on the MATLAB implementation, and that's it basically for lecture 16. Not a long one because most of them has been covered in lecture 15. Okay, so as always, if you have any problems regarding any lectures that you have, just feel free to come by and see me. Thank you.